Hey, welcome everyone. In this video we're going to be having a talk about polynomials and how to factorise them. Okay, and in the following video we'll go through some worked examples. Okay, so factorisation of quadratics. So we've got a few different options that we can use here. So perfect squares. Now for our perfect squares it can be a little bit tricky sometimes to spot them, that they can actually work. Okay, but the main thing you need to look at is whether your first term is a square, your last term is a square, and then we've got this middle term here, which is twice a times b. So if we've got a squared plus 2ab plus b squared, we can factorise that simply to a plus b squared. And similarly, if we've got a squared take 2ab plus b squared, that can be factorised to a plus b squared. Okay. Difference of two squares, we've got this time a squared take b squared equals a take b times a plus b. Okay, now that's quite nice and simple when we've just got a squared take b squared or x squared take y squared. Sometimes they can be a little bit trickier, which we'll see in some of the worked examples in the next video. Okay, now trial and error come into this a little bit with our quadratics. Okay, particularly when we look at x squared take bx plus c, what we're looking for is factors of c that add to b. Now of course we would have seen ones that get more complicated by having this a term there as well. And again, we'll look at some examples in our next video. Okay, for our cubics, okay, again, we actually have perfect cubes again. Now these are much harder to pick out. That's where we've got a cubed plus 3a squared b plus 3ab squared plus b cubed. And that can be factorised to a plus b all cubed. Okay. Now most of the time you'll be able to pick reasonably quickly that our first and last term are cubed. Okay, it's just whether these middle two terms meet our requirements. Okay, and again we can have a cubed take 3a squared b plus 3ab squared take b cubed. That gives us a take b all cubed. Okay, and again, just like we had our difference of two squares, we've got some in difference of two cubes as well. So a cubed plus b cubed, okay, can be factorised to a plus b outside of a squared take ab plus b squared. And our difference of two cubes is a cubed take b cubed equals a take b outside of a squared plus ab plus b squared. Okay. Now we've got a little bit more that we can talk about here as well. Okay, which is factorising cubics using grouping. Okay. So sometimes what we can do is we can group two parts of our functions, okay, and factorise them individually, ending up with a common term. Okay, so if we look at this one here, we've got x cubed take 3x squared plus 4x take 12. What we say here is this is going to be one group and this is going to be another group here, because we can factorise this quite easily by taking out this x squared term, which leaves us with x squared outside of x take 3. And similarly, we can factorise this just simply taking out the 4, okay, leaving us with our x take 3 again. This is important. There's no point doing this unless you get this common factor happening in both your groups, okay? Because this common factor now can come out, okay? So we end up with x take 3 outside of our x squared plus 4x. So it's whatever's left over becomes that second bracket, okay? Now we can also do a 3 and 1. Okay, now we won't do this as often because it's only certain times where this is really useful. Okay, but this one here, we could say this was one group and this is our other group. So we've got x squared plus 4x plus 4 take z squared. Okay, now here we've got a perfect square, and this is where this method can work. Okay, where we've got x plus 2 squared take z cubed. We've actually got difference of two squares there, so we can actually say that we've got x plus 2 take z outside of x plus 2 plus z. Okay, so a little bit of a unique situation where we do the 3 and 1. Okay, now we can also look at solving some equations. So we can use our null factor law. Now hopefully everyone's a little bit familiar with this by the time they get into this sort of stage anyway. Where we've got x plus a times x plus b times x plus c equaling 0. Okay, so we've already factorised it using one of our methods and we've set it equal to 0. So that means then, if we've got three things multiplied together and they equal 0, well, one or more of these have to equal 0. So it could be our first bracket, and we could say that x plus a equals 0, or it could be that x plus b equals 0, or it could be x plus c equals 0, or it could be all three. Okay, And then from there, we can hence get our solutions of x equals minus a, minus b, or minus c. So really, from up here, all we've done is we've switched our signs of our terms in there. Now, it can obviously get a little bit more complicated if we've got a coefficient here, but it's still just a matter of rearranging to solve it for x for each of those brackets. Okay? And we've got our quadratic formula. So that's where we've got ax squared plus bx plus c equals 0. Okay, then our solutions to that become minus b plus or minus the square root of b squared take 4ac on 2a. Okay, so we do get our true solutions to our quadratic equation, which we'd expect through this plus or minus part. So one solution will be your positive one in here, and your second solution will be your negative in there. Now we call this part under the square root sign here the discriminant, okay, represented by delta. Okay, if our discriminant is greater than 0, there are two real solutions. Okay, so we'll get two solutions for this quadratic. Okay, which would be a case where our graph crosses the x-axis twice. Okay, if our discriminant equals 0, then there is one solution. Okay, and that's going to be our case where we just come down and just touch our x-axis. Okay, so we get our one solution there. Okay, if the discriminant is less than 0, then there are no real solutions. So that's going to be caused by a graph that looks like this, or that looks like this. Okay, where we don't actually cross the x-axis at all. Okay, and it makes sense when we look back at what our discriminant is. Okay, it's this part here that's inside our square root sign. So if that part is less than 0, then we're going to be trying to take the square root of a negative number, which we know will give us no real solutions. Okay, so that's why that doesn't work. Okay, so when we're trying to solve a quadratic, okay, and it's one of these more complicated ones with our coefficients of x squared and x, okay, often it's just worthwhile just looking at this discriminant, just looking at your b squared take 4ac. It'll take you 2 seconds in your head, okay, to see what that number is. If it's less than 0, don't bother. Okay, you're just going to waste your time. Okay, because most of the time we're not going to worry about finding our solutions using this, because one of those previous methods is going to be a bit easier and a bit quicker. Okay, so in our next video we're going to look at some worked examples using this theory.